Good day and welcome back to the second part of our discussion on maximum and minimum values. In the previous video we introduced the associated terminology. What does it mean to have a local minimum, maximum, absolute maximum, and we finished up by making this connection to Calculus 1 where we saw that if you did have a local maximum or a local minimum at some value, then both the partial derivatives with respect to x and y at that point would be 0. And just like in Calculus 1, it turns out we're going to be spending a bit of time with optimization, which is going to require us to find these inputs, a comma b, where both the first partials are simultaneously equal to 0. And to give ourselves a bit of language to talk about these points, we refer to them as a critical point, which I will oftentimes abbreviate by CP, of a function of two variables f. So with this in mind, and because it is going to be an important type of computation, let's go through several examples of finding critical points, and then hopefully make some associated observations. For the first function f equals x squared plus y squared, to find the critical points we need to calculate the partial with respect to x, the partial with respect to y, and determine where are they simultaneously equal to 0. So the partial of f with respect to x is 2x. The partial with respect to y is 2y. And what I would like to know is what needs to be true in order for both of these first partials to be equal to 0. And note I'm fairly careful to put question marks above these equal signs just to indicate I'm not saying that first partial f sub x is always equal to 0. I want to solve, this is a question, for which values of x is this statement true. And we very intentionally picked a first example that works out extremely nice from a computational perspective. In our next few videos we'll see some examples that require a bit more algebraic manipulation. In this case, the only way that first partial with respect to x is 0 is when x is 0. And similarly, 2y is 0 precisely when y is equal to 0. Which tells us we have a single critical point at 0, 0. And note that completely answers the question that has been asked. Find the critical points of this function of two variables. But being the overachievers that we are, we will continue on to make an observation. The question remains that we can ask, is this a local maximum, minimum, or maybe even neither? There's no guarantee that at a critical point you will have a local max or min, as we've seen in our previous Calculus 1 experience. So let's see what observation we can make. If we substitute 0, 0 into our function, what we get back is 0. And for any input that we plug into the function, what we will always get back out is x squared plus y squared. And note, x squared and y squared are similar in the sense that a quantity squared is never negative. So the smallest it could ever be is 0. And note what we've really explained here. F of 0, 0 is less than or equal to f of xy for any possible inputs x and y. Which verifies for us that 0, 0 is not only a local minimum, we could even describe it as being an absolute minimum. So 0, 0 is an absolute minimum, and f of 0, 0 equals 0 is the absolute minimum value. So note in terms of the language and the terminology we use, the input we refer to as the absolute minimum or absolute maximum, as in where it occurs, and the associated output, the 0 in this case, would be that absolute minimum value. So 0, the number, corresponds to that value. And just for fun, let's even go ahead and think about this graphically. If I wanted to get an idea of what the sketch of this surface would look like, we would write z equals the function, x squared plus y squared, and then we can use the various techniques that we've encountered. But just a quick discussion, if I was to, for fun, cover up that y squared term, z equals x squared, i.e. thinking the y equals 0 trace, would be a parabola opening upward. Similarly, if we were to cross off that x squared, z equals y squared, now the x equals 0 trace, would be a parabola opening up upward. And in either case, they have a vertex at the origin. And hopefully what you see I'm getting at is that our surface is one of these paraboloids that we encountered back when we talked about quadric surfaces. So the work that we've previously done to help kind of identify and visualize graphs will certainly come in handy throughout our discussion. And we can very clearly see in our picture that at 0, 0, we do truly have this absolute minimum value. Okay, so let's look at another very similar example. We're going to make one, seemingly small, insignificant change. I'm going to take the plus sign separating the x squared plus y squared, and I'm going to turn it into a negative sign. And the question remains the same. Find the critical points, and then once we do, we'll talk a little bit about those critical points. So in this case, to find the critical points, we need to know where is that partial with respect to x and the partial with respect to y, both simultaneously equal to 0. And the only difference in this case would be the minus sign associated with the f sub y, but in either case, f sub x is 0 when x is 0, f sub y is 0 precisely when y is equal to 0. So we again have a single critical point which occurs at 0, 0. And we can also observe that the output at 0, 0 is still 0. And what I would like us to do is to try to imagine what the graph of this function of two variables would look like, i.e. the corresponding surface if we were to sketch it, and see if we can somehow classify this critical point, much like we've done above. And it turns out that this is a fairly challenging surface to visualize, and to help us do so, I'm going to draw two traces, and then we'll turn to a little GeoGebra animation. So in terms of some traces, going back to our method that we encountered with quadric surfaces, if you were to look at the x equals 0 trace, the x equals 0 trace for the surface z equals x squared minus y squared would simply be z equals minus y squared. And graphically, this is going to be a parabola in that x equals 0 plane, i.e. flat on the screen in the yz plane, with a vertex at the origin, and it is opening downward. So from this single x equals 0 trace, if we were to have a local max or a local minimum at our critical point of 0, 0, which one would it be? And yeah, I agree. If it is one or the other, it's going to have to be a local maximum from what we see. But hold on, let's look at another trace. If we look at the y equals 0 trace, we would get z equals x squared, which note is also a parabola with a vertex at the origin. Now we're thinking in the y equals 0, i.e. xz plane, and it's a parabola going through the origin, opening up around that z-axis, going upward. And if we were to only look at that y equals 0 trace, our guess would be that we have a local minimum. And it is impossible for a critical point to simultaneously be a local minimum and a local maximum as we've sketched to the right. So in this case, I'm going to make the observation that 0, 0 is not a local maximum. And whenever we have a critical point which is not a local max or a local minimum, we call that critical point a saddle point. So we call 0, 0 a saddle point. And note, we have not sketched the corresponding surface. We've simply sketched enough in terms of traces to draw the desired conclusion. But just to give you an idea of what this surface would look like and why we might actually call this a saddle point, let me embed a little bit of GeoGebra footage. The surface that we now have pictured, created in GeoGebra, corresponds to the graph of z equals x squared minus y squared. And as I hit play, we're going to investigate this surface. We have our critical point at the origin, and the first trace we're going to look at is the x equals 0 trace. And note, in that x equals 0 trace, you get this parabola opening downward with the vertex at the origin. So very clearly that would be a maximum type of behavior. Similarly, if we look at that y equals 0 trace, we now have a parabola opening downward with the vertex at the origin. So our critical point at 0, 0 cannot possibly be a local maximum or a local minimum. But note, this might give you a little bit of intuition as to why we would refer to this as a saddle point. You could almost imagine, sitting on this surface, much like you would sit on the saddle of a horse. And I'd like to finish up this video with an observation. In the first example, we classified our critical point as a minimum purely by graphing the surface and making the observation. Similarly, in the second example, we classified our critical point as being one of these so-called saddle points by a graphical investigation. And that presents us with a problem. The more complicated our function of two variables becomes, the more difficult this graphical investigation will be. So instead, what we need is a more computational approach to classifying critical points as a local maximum, a local minimum, or now a saddle point, which is the topic of our next video. So stay tuned and take care.